best budget impact driver. If you've ever found yourself saying, "Self, what is the best budget impact driver?" Well, hopefully this video will answer that question for you. So budget impact, that's of course subjective, but budget for me is under 50 American kopecks. You can plug each of these instruments from their operative location and then call it your own. So how are we going to compare them? Well, we've already raced them. And I've got a plan. My plan is to break down each of the races and then do a more in-depth review of the tools that competed against one another, right? And I've already worn both of these tools asses all the way out. So this one farted the smoke out, burn it up. This one stalled out, tested it to its absolute limit. And ever since then, it just ain't got no jam. So if you've asked yourself, can you test the tool to failure where the safety cuts it off? Will it recover? The answer is negative, not for this tool. This tool has been sick ever since I ran it all the way down. And then, yeah, so after that happened, the tool never fully recovered. The Ryobi did, ironically enough, but this one didn't. And I just haven't, I wouldn't buy this tool if I had the money to spend on the tools. I just bought it to review it. It was actually on clearance at the Horrible Freight, so I was like, hey, why not? I'll add that to my entourage. So what are the tests? Well, I have a specific interest in what I want to test. And what I want to do is I want to compare the box spec propaganda, so the BS, the marketing wank slap on the box to, you know, compel you to buy the product versus real world specs. And I've tried to devise different tests to come up with these different things. And right off the rip, what we're going to do is we're going to use the power analyzer and see if we can't determine what the real world wattage pool of each of these tools are versus the wattage that they claim wattage outputs. Okay, and interestingly enough, the Ryobi did 547.1 watts versus a meager 425 is what the operators said that it actually did. That's a strange decision. Why would the marketing people claim less than what the tool actually pulled? All right, next on the list we have the Rigidity. Okay, and it did an underwhelming 473.8 versus a 380. Again, that's a very unusual decision. Why would they underrate it by almost 100 watts to doodles? Anyway, so moving on to the Bauer. And we have 450.7 versus 350. So this begs to question, do they even test these tools? Why would all of them be 100 watts under what they said they were? And it's you know, it's like you would build a car and say that it was not nearly as high performing as it actually is. I don't understand. I don't have a marketing background, but I can't, my small little mind can't factor that into something reasonable. So the next test we're going to perform is we're going to compare the box RPMs, no load speed of the tool versus the actual RPM speed of the tool. So here we go. So 2415, that does not seem like as much as what they're claiming on the box. But of course, I blew this. I've already ran this one to the limits. I've tested it to failure, so it might have lost some chooch during that period. This one, I also ran this one hard and put it up wet a couple times too. in my professional opinion, or my opinion, it's probably not professional, but in my opinion, the Ryobi is a superior tool all the way around. There's actually no comparison. So 2940 something. That's about right in line with the box specs say. And then we'll check out the Village Idiot here. So 2660. That's not too bad. And again, it's just and then that's it. There we go with that. None of them actually matched the box specs, and of course the instrument that I used to evaluate the speed, it could have been weight. They could have just measured. I mean, that could have affected a couple RPMs. I wouldn't imagine that it would have thrown it off quite like it did. But anyway, who knows? So the next test, and the most fun test, is we're going to peel back the petticoat and see what's under the dress. So, this is not the right direction to open them. Let me do the old flipperoonie. And then we're going to get into the goods. So, I've already cracked the top on all of these, so I'm familiar with what's inside of them. We won't have to be farting around trying to figure. So the first thing that I want to do is compare the quality of the injection mold. And right off the hop, this is just an astonishing amount of complexity. Why would they put all this complicated geometry in such an inexpensive tool, right? You know, they have this closed cell foam to provide a little bit of cushion for the brushed motor as it bounces around while you're wiggling and jiggling. And then, of course, this is about as cheap an injection molded part as you're going to find. So they're all PA6. See the PA6. And then this one is the PA6. And this one's also PA6 GF30. So glass fiber, 30% glass fiber by weight. So it's fiberglass reinforced nylon. That's the bog standard for all of every tool that I've ever taken apart. Basically has the same build material. And then the overmold, right? So this is TPS, so thermoplastic styrene. This is also thermoplastic styrene. And then this is TPE, so thermoplastic elastomer. And if I'm not mistaken, the TPE is butylene, so it's a softer rubber. These are a little bit harder. Styrene is a nitrile rubber. What it is it's actually found its home in gloves. So people that have problems using latex gloves, they break out. They have nitrile rubber gloves that are substitutes, and this is that. Another big deciding factor in the comfort is how much meat they squirt in there. So you can see there's a lot more wall thickness for the rubber of these versus this. It's just an economical design decision. And then this mold has got some funk marks on it. You can see how grungy it is. This glass fiber is really hard on the die and the mold. When it skeets it out, it eats it up, so it gets all stanky over time. Oh, speaking of stanky, butylene. So if you're a mechanic, you might want to stay away from butylene because there's a chemical reaction that occurs when you subject this to petroleum, right? So if you get petroleum on butylene, it starts to off-gas butyric acid, and that's the nasty reek that comes out of human vomit. It's the exact same chemical. So if you get petroleum on this, it starts getting hemorrhoidy and bubbly and nasty, and it also starts to stink to high heaven. So, you know, might want to factor that into your purchase decision. When it comes to pure comfort, I would say the Rigid is the most comfortable, with the Ryobium in the second place, and then this is just horribly uncomfortable. It ain't got nothing there's, you know, the overmold is, there's not much there. It's almost like holding plastic. Even though it's soft, it's just, there's nothing to it. Okay, so moving on down the line, we're just going to start with the Bauer. And interestingly enough, they put this complicated circuit board, doing circuit board things. I don't know why they would do that. The way that they control the speed of these motors is with a pulse width modulator. Right? You can't just adjust the flow of electrons, the voltage. That will control the speed of the tool, but you ain't got no torque if you do it that way. This is a PWM that I'm going to talk about in another video coming up. How they control, like the wizardry, the digital wizardry associated with controlling a tool speed has always fascinated me. I'm not going to get into it, but I'm fairly certain that's what this is. You know, you can see these two MOSFETs. They appear to be in an H-brick configuration, and then you've got this little brain down there doing a lot of circuits, a lot of brain things. And then these two leads right here go to the headlight, so you can, they got the tri-headlight design. And then surprisingly enough from this tool is there's a lot of name brand components. So this is actually a J-level switch. It's a potentiometer switch. It's got a great feel. And then the most astonishing thing of all is this is a Mabuchi Japanese branded motor, son. About as good as it gets. It also baffles me again. Why would they put such an expensive electronic drivetrain in this thing? Look at that. It's pinched it. I might have pinched it. Somebody pinched it. But it's you know, this is a very expensive DC motor, and it's got the enclosed brush assembly, everything. And then another interesting part of this is it's got this cast aluminum hammerhead assembly at the top, right? These are powdered metal gears. I wouldn't expect anything less, you know, but it's got this pinion, and then they had this, you know, very expensive part to manufacture. They did some face milling, surface milling, quite an expensive piece for such a cheap tool. They probably buy them by the bajillions. They just have them, so they use them. Now next we're going to compare the Rigid versus the Rhodium. And they're both made by the same manufacturer. So the corporate overlords, TTI, is a Chinese brand, and they license these different tools. And you know, you're talking about, like, these are the overlords. They control like 25-30% of the global tool market. They also own Milwaukee and probably several others. They're big monster companies. So it wouldn't surprise me to see a lot of the same components. And these switches are identical. They feel the same. They just put different buttons on the surface, so you can see the buttons are different design. These have got ribs for, I guess, for his pleasure. But they feel exactly the same. And then you've got the these little terminal. They're probably nickel plated. Nickel is a good conductor. And they've got these staked on leads. And then the Zeode potentiometer. Feels good. It's not a bad feeling potentiometer. Let's compare the size of the hammer. And it's a little smaller, this one. So baby. So obviously this is going to impart more, it's going to transmit more inertial force into the hammer or the anvil down in there to spin the bit and the fastener around. And then they both are, obviously they're brushed DC motors, but what's cool about this one is we can pop it apart, and it'll give me the opportunity to really try to explain how these DC brushed motors work. So on the ass end you have the commutator the brush. And what's interesting about this is a quad brushed assembly, right? Normally there's only two. Whoopsie doodle. Like this one. See, there's only two brushes on it. Also, another economical minded design decision is, instead of using the solid roller bearings for the to support the rotor, they used oilite, so oil impregnated bronze bushings for this one. It's just another cheap design decision designed to save money. But obviously these cheaper pieces does not translate into more or less power. This is the more powerful unit. It's a bigger, physically larger motor. And then you have, back where we were, so you have this quad brush assembly, and the way they work is you have the commutators right here, the comm bars, and those comm bars interface with the armatures. So, and these armatures are actually stacked laminates. So if you can see, there's like probably 100 or so little laminate shims stacked together to create the armature, and then they turn wires. And from the world of racing RC cars, there's a lot of complicated terminology and stuff that goes into this. But one of the most interesting technical aspects of these motors is, so the number of turns, so the number of copper turns that go around each of these armatures dictates the performance aspects of the tool or the motor specifically. So the fewer turns, the lower resistance of the electrons flowing through it translates into a higher speed tool. So you can imagine like a 4-turn brushless, and I'm sure that applies to brushless, or a 4-turn brushed DC motor means the electrons can flow through it with very little resistance. And that, like I said, that translates into an extremely high-speed motor, but low torque, right? The magnetic field is weaker. It's just the electrons are literally flowing faster through it. So it's alternating, it's turning it faster. So it switches the power on and off at a certain speed. And when it switches, it electrifies the magnetic field. And they're always parallel. So when it's on the stator, the magnetic stator ring, so these are permanent fixed magnets, probably neodymium magnets. As it turns in this stator, it actually turns one set on, and then as it turns, it'll turn the next set on, and it creates an electromagnet, and this electromagnet actually spins it inside the stator. So the number of turns of copper wire around each armature, the fewer turns, the higher speed, but the lower torque. So like a 24-turn motor would have a lot of torque and it wouldn't have a lot of speed. So interesting. And you see this glob of epoxy, that is to balance it. Normally they take chunks out of the laminates, out of the armature laminates, and that's how they balance the motor so it's not wobbling around inside the stator. And then it's got this big beefy pinion on the end versus the little dinky pinion on this one. And then what kind of pinion are we talking about here? I think it might be the exact same pinion, actually. They all operate under the same pretense, so there's single speed reduction. You've got the pinion gear goes in, turns the planetaries. The planetaries measure the single speed reduction as the planetaries turn against the ring gear, and then that's how the speed is controlled. And then I'm sure that these they have a physical connection, because DC is only, technically it's only 2-phase or single phase instead of Yeah, yeah. So there's a physical connection. So it alternates. Joop, 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 joop. And that's how it spins, you know, that's how it spins the commutator. So you can see these comm bars, and they're already, you can see the heat that I've already heated them up quite a good bit. And then this is a nice high quality part. But always that's a, you know, it's perfect that it doesn't always translate into more power. Absolutely. Very expensive little motor, but it ain't got no gut. And then this one is the most powerful of all, and the reason is it just boils down to physical size, right? It's just a bigger unit. Even though it's a cheaper design, two brush assembly. Let's see how angry this thing gets when I crank it up. So you can see the brushes. And you see that inductive kickback? There's got to be some electronic components in this battery designed to, there's capacitors or either a diode, a one-way diode that keeps it, because that inductive kickback from these brushed motors are nasty. It'll burn everything up, absolutely everything up. It's probably actually inside of this unit. I'm going to take it apart. Yes, let's take it apart. Now we're in. So there's a MOSFET. That does the switching. And MOSFETs, they're just big old, yep. So there's the diode that I was talking about to mitigate the induction kickback. So when you let off the trigger of a brushed motor, you get that big surge of power that runs back down the circuit. And so this is basically a one-way check valve. And these brushes are more than likely, they're probably carbon graphite. For 945T. I don't know what that is, but I'm going to look it up. Okay, so that's it. If you want to see my review, go to the website, review.wfskills.com. If you have these tools and you don't agree with my reviews, leave your own reviews. You're welcome to come on board and be a part of this little community that I'm trying to build. So the best tool, this is the best tool of the bunch. This is the second best. This is the third best, with a surprising number of high quality components. Till next time.